Welcome students. Today I am going to discuss another part of unit 2, that is electric propulsion unit of the subject electrical and hybrid vehicle. PEEE 602A is the subject code. Today's topic of discussion is a discussion about the control of BLDC and SRM motor drives. Permanent magnet BLDC motor drives. So what are BLDC motors that we need to understand first? So, BLDC motor and its construction. So, as we can see, that this is a cross-sectional view of the permanent magnet rotor, which can be surface mounted and interior mounted. So, BLDC machines are categorized by the position of the rotor of the permanent magnet geometrically according to the way in which the magnets are mounted on the rotor. The magnets can either be surface mounted or interior mounted. So we can see that this figure here, it's a surface mounted permanent magnet rotor. Each permanent magnet is mounted on the surface of the rotor. It is easy to belt, and especially skewed poles are easily magnetized on this surface mounted type to minimize the cogging torque. But there is a possibility that during high speed operations these magnets can fly away. So basically, we have this another construction, which is the interior mounted permanent magnet rotor. Here the magnetic poles are mounted interiorly, and so we do not have a problem during high speed operation. Now, how we control the BLDC motors? So the basic principle of BLDC motor drives is shown in this particular figure. The BLDC motor drives mainly consists of the BLDC machine. So this is a BLDC machine. The digital signal processing controller, that is the DSP. The power electronics based converter. So this is the power converter. The position sensors are there, that is H1, H2 and H3. These are known as the Hall sensors, which sense the position of the machine rotor. The rotor position information is then fed to the DSP based controller, which in turn supplies the gating signals to the power converter by turning on and off the proper stator pole windings of the machine. In this way, we can control the speed and the torque of the machines. Now, this is the block diagram for the torque control of the BLDC motor drive. So, what happens here? Let us see. So, this is the BLDC motor. In vehicle traction application, the torque produced is required to follow the torque desired by the driver and the commanded through the accelerator and brake pedals. Thus, torque control is a basic requirement. This figure shows the block diagram of the torque control. The desired current IS reference is derived from the commanded torque, that is the T reference, through a torque controller. So this is the torque controller. The current controller and the commutation sequencer receives the desired current IS star, the position information from the position sensors, and perhaps the current feedback to the current transducers, and then produces the gating signals for the three-phase inverter. These gating signals are sent to the three-phase inverter, which produces the desired phase current for the BLDC machine. So this is a typical block diagram of the torque control of a BLDC motor. Now we move on to the block diagram for the speed control of the BLDC motor. In traction application, speed control may also be required. Many high performance applications include current feedback for torque control. At the minimum, the DC bus current feedback is required to protect the drive and the machine for the information current. So this is the BLDC motor, the position sensor, the current control and the commutation sequencer. Then we have a speed sensor. And then we have a speed controller, which ultimately provides us with the desired torque, and the other part, as we can see, is almost similar to that of the torque control. The controller blocks, that is speed controller, may be any type of the classical controller, that is PI controller, or maybe some advanced AI based controller. The current controller and the commutation sequencer provides the properly sequenced gating signals to the three phase inverter, while comparing the sense current to a reference to maintain a constant peak current control. And this peak current control can be done, that is a current controller can use the hysteresis control or a voltage source PWM based current control for providing the gating signals. Using the position information, the commutation sequencer, what it does, it causes the inverter to electronically commutate, acting as the mechanical commutator of the conventional DC machine. The commutation angle associated with the brushless motor is normally set so that the motor will commutate around the peak of the torque angle curve. So if it's a three-phase motor connected in delta or star, commutation occurs at electrical angles which are plus or minus 30 degree from the peak of the torque angle curve. When the motor position moves beyond the peak, then an equal amount of 30-degree electrical, then what we do is that then the commutation sensor causes the stator phase excitation to switch or move the motor suddenly to minus 30 degree related to the peak of the next torque angle curve. So in this way, we basically control the torque and the speed of a BLDC motor drive. Now moving to SRM, that is switch reluctance motor drives. So this is a typical SRM drive control. A conventional SRM drive system consists of the SRM, the power inverter, the sensors such as voltage, current and position, and the control circuitry such as TSP controller and its peripherals. Through proper control, high performance can be achieved in the SRM drive system. The SRM drive inverter is connected to a DC supply which can be derived from the utilities or from batteries. The three-phase windings of the SRM are connected to the power inverter as shown in the figure. The control circuits provides the gating signals for the switches of the inverter according to the power control strategies or particular control strategies and signals from various sensors. So what typically SRM motor is? So this is a cross section of a typical SRM conversion, that is a 6 by 4 SRM or 8 by 6 SRM. So 1, 2, 3, 4, 5, 6, and here are the 4 poles 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6, 7, 8. So the stator has 8 and the rotor has 6 poles, or the stator has 6 and the rotor has 4 poles. So the SRM has salient poles on both the stator and the rotor. It has concentrated windings on the stator or permanent magnet on the rotor. There are several configurations depending on the number and size of the stator and rotor poles. The most common configurations are 8 by 6 and 6 by 4. Now coming to the SRM drive converter. So the SRM drive converter is typically a classic converter. So what we do is that how the classic converter use, the main advantage of the classic converter is the flexibility and control. All the phases can be controlled independently, which is essential for very high speed operation where there will be considerable overlap between the adjacent phase current. So what is the classic converter? We can see here. So the operation of the classic converter is taken in is shown in figure 13 by taking one phase, that is a phase 1. There are several phases as an example. When the two switches, that is S1 and S2, they are turned on, the DC watt voltage VDC will be applied to phase 1 winding. The phase 1 current will increase as it flows through the paths consisting of VDC positive terminal, then S1, then phase 1 winding, then S2 and the VDC negative terminal. When we turn off S1 and hold on to S2, that is here, so the current free wheels through S2 and D1. In this mode, phase 1 is not getting or giving any energy. So this is the zero voltage mode. When S1 and S2 both become when S1 and S2 both become off, then the phase 1 current will flow through D2 and the VDC positive terminal and the VDC negative terminal, and then to D1 and to the phase 1 winding. During this time, the motor phase is subjected to negative DC watts voltage through the freewheeling dials. The energy that is trapped in the magnetic circuit is returned back to the DC link. The phase current drops due to the negative applied voltage. So how we regulate the phase 1 current by turning off switches S1 and S2. So this is for phase 1. We have the same kind of configuration for the other phases also, phase 2, phase 3, phase 4, phase 5, phase 6. So a classic converter works in these three modes of operation, that is the turn on mode, the zero voltage mode, and the turn off mode when the energy is given back to the supply. That is, here the SRM drive can act as a SRM generator, or the switch reluctance generator, and it feeds the energy back to the supply and can be useful in helping charge the DC supply source, that is the batteries.